So today we're going to be looking at the work done by a force. So first we need to define what we mean by the word work. So in mechanics we're thinking about mechanical work. And this is done by a force and it causes an object to move. For mechanical force to happen, we need the force that causes motion, and we need motion to occur. So for mechanical work, we need the force and we need motion. If we don't have both of these things, we don't have any mechanical work. So if we think about a weightlifter, and the weightlifter is lifting a weight up, there's mechanical work. There's the force from the muscles, the tension in the muscles, and there's motion. But when the same weightlifter is now holding the weight above their head, there's no work. Even though the weightlifter is putting a lot of effort in to hold this weight above their head, there's no motion, so there's no work. When we talk about the line of action, this is the line of action of the force, and it's the same direction as the force, and it includes a point of application. So let's think about two blocks. This is the start point, so this is the start, and it's moved some distance, which we're going to call D, to this point here, the end point, by some force, and that's in newtons, and the distance is in meters. So the work is the force times the distance. We can also think of the distance as the same as displacement, but work is a scalar quantity. However, it can be positive or negative. If you look at the units of force and distance, work is going to be measured in newtons meters, but we actually, in SI units, we call 1 Newton meter is the same as 1 joule. So 1 Newton of force will move, 1 joule is the same as 1 Newton of force moving an object 1 meter. Joule is the SI unit that we use for work. Now let's look at an example. A boy uses a constant force of 250 newtons to push a box of 4 meters across the floor. Find the work done by the force. So work is F times D, and that's 250 times 4, which is going to be 1000 joules. Let's look at another one. A girl holds a mass of 20 kilograms above her head. Find the work done. So the mass isn't moving, so no work done. So the work is 0 joules. A ball of mass 0.05 kilograms falls a distance of 1.5 meters. Find the work done. So if we consider this ball, its mass is 0.05 kilograms. So the force is going to be the same as the weight, which is mg, which is going to be 0.5 newtons is going to be the weight. So the work is the force times the distance, which is 0.5 times 1.5, which will be 0.75 joules. Now, in this situation, the force is, the weight is falling, the mass is falling down by the weight of the object. So when an object falls by the weight, this is referred to as work done by gravity. When an object or when a force acts and the direction of motion is upwards, for example, our weightlifter lifting the weight, we say the work done is against gravity. Now, sometimes the direction of motion is different to the line of action. So let's consider a canal boat. So the canal boat's in the canal. Here's our little boat. And it's on a tow, its direction of motion is this direction. But the force is caused by a pulling force on a tow rope. And we have the contact force of the boat along the side of the canal. And this is the direction of motion. So in this case, the line of action is the same as this, in the same direction as the pulling force, but the motion is here. And so what we do in this situation, we need to resolve the forces so we can calculate the work done. So we would resolve the components in the direction of motion perpendicular to the direction of motion. So let's have a look at that. So let's consider again our block. Oh dear. And it moves this distance from here to here. And it's been moved by a force at angle theta to the parallel, to the horizontal. So what we would do is we need to resolve the components of that force. So we have the perpendicular, which is F sine theta, and we have the horizontal, which is F cosine theta. And because we want the component of the force in the direction of the motion, the work, which is the force times the distance, well, it's this force which we're interested in because this is in the direction of motion. So we would have the work in this situation when you resolve the components is going to be F times D times cosine theta. Let's look at some examples where we're going to use this. So a small truck is pulled 5 meters along a rail track by 100 newtons of force at an angle 60 degrees to the track. Find the work done. So we know work is going to be FD cosine theta. The force is 100 newtons, the distance is 5 meters, and it's cosine 60. And that will give us 250 joules. Now, if there's a force opposes the direction of motion, the work done by this force is negative. We say it's done against the force. This happens, for example, when a load is being raised vertically. The work is being done against the weight, against gravity, as it is. And we're going to look at an example where this is the case next. So, a ball of mass 0.05 kilograms raised through 1.5 meters. Find the work done against gravity. So the weight is going to be 0.05 times 10, which is 0.5. So the work done against gravity is going to be force times distance, is going to be 0.5 times minus 1.5, which is equal to minus 0.75 joules, because it's going against the gravity. When several forces act on a body, we can add the work done by each force to get the total work done. When you're doing this, remember the work done can be positive or negative. Remember, if it's negative, the work being done is going to be against the direction of motion. You may also need to resolve the components of force into the direction of motion. And we'll look at an example of that next. So we've got a box of mass 5 kilograms. It's pushed up a slope of incline 30 degrees. To the horizontal by a force of 30 newtons at an angle 10 degrees to the slope. The frictional force acting on the box is 2 newtons. The box moves 3 meters up the slope. So firstly, we want to find, don't know what I was writing there, the work done against friction. Find the work done against gravity. Find the work done by the push force. I want to find the work done by the normal reaction. And finally, we want to find the total work done on the box by all the forces. So, part A, the work done against friction. Is going to be F times D. So the force of friction is 2 newtons and it's going 3 meters. So that's 6 joules. Now, note the friction acts along the direction of motion. Oh, we're going to have to draw, actually, before we start. We will draw a force diagram. In these situations, always draw a force diagram. So the incline is 30 newtons. And here's our box. And we've got the weight coming down. And that's going to be 5 times 10, which is 50 newtons. Now we've got our friction, 2 newtons, and that's in the same, it's parallel to the slope. Now we have this push force, and the push force is in that direction, but there's 10, it's not to scale, 10 degrees to the slope. The reaction, normal reaction, is perpendicular to the slope, that's R. So B, the work done against gravity. So we need the component of weight down the slope. So we have our slope here, there's our weight, and it's 30 degrees. So it's going to be our weight, which is 50, times sine of 30 is going to be 25 newtons, and that's the component of the weight that's acting down the slope. So the work done against gravity is F times D is 25, and again we're going 3 meters, which will give us 75 joules. Now part C, we'll do it here. The component of the push force is going to be 30 cosine 10, because we've got 30 newtons of push force, and it's the component of the push force to the horizontal of the direction of motion. So that's cosine 10. So it's going to be 29.54 newtons. That's the component of the force. So the work is FD. So it's 29.54 times the distance, which is 3, which will give us 88.6 joules. And D, find the work done by the normal reaction. So there's no movement in the perpendicular. So no work done by the normal reaction. So let's now find the total work done. I'm going to have to get a new page up here. So the total work is going to be the work by the push force minus the work done against gravity, because that's against the line of motion, minus the work done against friction, So we had 88.6 joules from the push force, we had 75 joules from against gravity, and we had 6 joules against friction. So that gives us 7.6 joules of work done altogether. Finally, just to note, sometimes a question might mention non-gravitational resistance. This means all the components of forces such as friction, air resistance that act against the motion. It does not mean any component of the weight that would oppose the motion of a body travelling uphill or rising vertically. So it's just important to bear that in mind. So I hope that helps.